So this video is going to be the mole review sheet plus a little bit of practice trying to help you guys get to that point. Of course, in this entire unit we've spent a lot of time discussing what the heck these moles things are. And we've come up with two primary ratios that represent a mole. First ratio involves Avogadro's number. So 1 mole of any compound is 6.02 times 10 to the 23rd particles of that substance. And in your calculator, anytime you see scientific notation, there's that fancy letter E in there. And so if I have 1 mole of iron, I have this many, 6.02 times 10 to the 23rd, iron atoms. If I have 1 mole of, I don't know, carbon monoxide, that would be 6.02 times 10 to the 23rd carbon monoxide molecules. I say molecules because that's carbon and oxygen put together. It's not one atom, it's a molecule. But 1 mole is always a certain number of pieces or particles, and that is Avogadro's number. That's how many. That's how many. When you talk about Avogadro's number, you're really talking about how many pieces there are. You know, how many pieces. Now, how heavy, but how many? You know, same as if I said, I've got 55 cats running around my house. I do not, for the record, have 55 cats, but that would be telling you how many. Some people might convert 55 cats into dozens, and they'd say that crazy guy has a little bit over 4.5 dozen cats. Oh my gosh, 4.5 dozen cats? That's a lot of cats. But we use this huge number, 6.02 times 10 to the 23rd, because atoms are tiny. We need a big number to encompass all of these tiny pieces at once. And that's where Avogadro's number comes in. The mole also represents the masses on the periodic table. Even Lady Gaga gets that. And so when you go to the periodic table and you look up a particular element and you see its mass on there, let's find an element on this periodic table. Whoa! You can't read any of these masses, that's a fail. But if you look on your periodic table and you find, I don't know, sodium. Sodium says 39.10 grams for its mass, so that represents 1 mole of sodium. But what if I have a compound like carbon monoxide? Well, you have the 12 grams from the carbon, and then you have the 16 grams from the oxygen, so carbon monoxide 16 plus 12 is 828. Be 28.01 grams for 1 mole of that molecule. So we go to the periodic table to find the mass of a mole. And because these are the masses of a mole, they are called molar masses. You're going to search the periodic table lots and lots and lots and lots and lots during the test, during homework, during practice, yada yada. So let's look at some molar masses. The first couple questions on your review sheet were find the molar masses, which are measured in grams, or grams as most people say it. And we just go to the periodic table, we grab the elements and add them together. So this one has 3 hydrogens, so I took hydrogen and I multiplied it by 3. It has 1 phosphorus. I went to the periodic table and I found phosphorus. I didn't have to multiply it by anything because there's only 1 phosphorus. And then I found oxygen. Oxygen is 16. There's 4 of them, so I multiplied by 4. And then I added all of these pieces together to get the molar mass of H3PO4. And that is where this answer came from. That is H3PO4. You know, now that I look at it, I feel like that is actually a little light. Let me grab my calculator and check that math. I'll be right back. My suspicions were correct. I just added these together in my calculator again, and it actually comes out to 98.01. I'm not exactly sure what I had done wrong the first time. So 98.01 grams is the mass of 1 mole for phosphoric acid. Cool. The next one's not worked out, so I guess I'm going to have to work it out. I am going to go to the periodic table a whole lot, and to save you all the horribleness that is my handwriting with the Promethean pen, I'm going to type it. So we have 2 potassiums, that is 2 times 39.10. And then I'm going to add that to the 4 carbons, well 4 times 12.01. And then I'm going to add that to the 4 hydrogens, and that's 1.01. Oops, 1.01. And then I'm going to add that to the 6 oxygens, which each one of them come in at 16.00. And so those masses, again from the periodic table, added together, equal the molar mass, which, as you can see just above in black there it's listed. Oops, that's the wrong thing. There we go. Right here is the molar mass after all of that gets added together. Okay? Number 3, same idea. I want to point out in number 3 that there are parentheses around the C2H3O2, also known as your friend acetate. And when there's parentheses, you need to distribute, meaning multiply, the number that's on the outside to everything inside the parentheses. Since there's a 3 on the outside, we have to triple everything. That's why there's 6 carbons. That's why there's 9 hydrogens. That's why there's 6 oxygens in this work over here, because they multiplied these values by 3. Now, did they multiply the iron by 3? No, the iron is not inside the parentheses, so it does not get multiplied by 3. So after you find all these values and you grab a calculator and you add them together, please don't try to do this in your head. Use a calculator, and now you've found out how much mass 1 mole of this particular compound is. Each compound has its own molar mass, or mass that represents a mole, and you just have to go and grab the pieces, put them together, throw them on the table. Number 4, we have 2 galliums, 3 sulfurs after you distribute the 3, 12 oxygens, because 3 times 4 is 12, last time I looked. Then you have to add these pieces together. 2 times gallium plus 3 times sulfur plus 12 times oxygen. And it looks like it comes to 427 grams, which represent 1 mole. Number 5 is nitric acid, HNO3. So we have the H, the N, and the O3 all being added together very carefully. Number 6, our good friend carbon dioxide, so that's 12.01 grams for the carbon, plus 2 times, what's the mass of oxygen again? That's right, you're right, good job. Hey, I like your hair today, looks good. Yeah, oxygen 16, good job. So we add the carbon and the oxygen together, and that's how we get the mass of carbon dioxide. Cesium chloride is CsCl. I don't know the mass of cesium off the top of my head. I'd have to look it up on something called the periodic table. Then I can add those pieces together, cesium plus chlorine, and that's where I got the 168.36. And the same thing's going on with number 8. All 8 of these were just find the molar mass. You're going to have a section just like this at the very beginning of your test. Write down the molar mass, write down the molar mass, write down the molar mass. Hey, you should probably write down the molar mass. And again, that's just adding the pieces together off the periodic table to represent the mass of a mole. We move on to the second section here, and from the get-go I realized that there is a minor issue. Remember earlier when we saw phosphoric acid? I'll go back and find it for you. We said that phosphoric acid was actually, right here, 98.01 grams for a mole. But this fool, he wrote 97 98.99. So you know what? I've already taken a point off of this kid's grade. Little Russell losing points for making silly mistakes. I've already taken a point off this kid's grade because he is 97.99 instead of the correct 98.01. So later on, when Russell uses 97.99, he's just reusing that value, and his mistake has already been assessed. I've already taken a point off for that mistake, haven't I? So Mr. Murphy is not going to take a point off of Russell's grade because he's already done that once before on this test. So let's see what he did do. In fact, let's actually just erase that and do it the right way. Alrighty. You know what? I'm going to pause the video and write some stuff. So we have 0.3 moles. So I wrote my given 0.3 moles. And then I wrote 1 mole on the bottom, just using the principles of dimensional analysis here. And then I need to write the molar mass on top. Because I'm trying to find grams, grams should be on top. And as we saw a minute ago, the right molar mass is 98.01. So I have my given, I have the correct ratio in my dimensional analysis set up correctly there. Then I do 98.01 times 0.3, and the calculator is going to give me 29. And again, that's H3PO4. So 29, that is 29 grams of phosphoric acid. I can hear someone thinking about significant figures. This value right here had 2 significant figures. So in my answer, I'm only showing 2 significant figures. I would not worry too much about significant figures. I'm only assessing a couple of points on the entire test for that. Most of the test is the dimensional analysis, is the molar mass, is the units and things. That's where my focus would be. If you have extra time and you want to go back and check sig figs, do that. But I am not going to talk about significant figures again during this review sheet. I say not. I know I'm going to, but I shouldn't overemphasize them. Sorry if I do. Let's go to number 10. Number 10. We have 12 moles of K2C4H4O6. And there we have the molar mass, 226.27. Where did that come from? Well, let's go back. Look, there it is right there. K2C4H4O6, and it's being used in another question. So again, a lot of the molar masses that you work out in the first section of the test will be used later on, so you don't have to keep working the answer again and again. And as we saw with Little Russell, if you've already had points taken off for that part mistake, you're not going to have further mistake points taken off. This guy has 12 moles. He wrote it down. Then he used the mole ratio. 1 mole is equal to the mass, or molar mass. He multiplied 12 by 226.27, and he got the answer. He also rounded it based off of some rules we discussed already. I'm going to do 11 and 12 on the next page in just a second. But while I'm on this page here, let's look at number 13. Number 13 has different units to start. These all started with the unit of moles, or M-O-L-E-S. This one is starting with particles instead. That's a different unit. And so, when we get a different unit, we have to ask ourselves, are we using 1 mole and the molar mass, or are we using 1 mole and Avogadro's number? Those are the only 2 choices you have. Well, since this is particles, we're going to use the 1 mole and Avogadro's number ratio. That ratio will allow us to change the weird, huge number of particles into moles. I have given you this advice at least thrice, but here we go again. put parentheses around values that are in scientific notation when you enter them into your calculator. That way your calculator will know what you mean. So 4.2 times 10 to the 24th times 1 divided by Avogadro's number, that's only going to give us moles because these particles and those particles cancel, and now we've got moles. But the question clearly asks for mass, which means we have one more step to go, and that last step is just changing moles into grams using the periodic table. The 56.11 came off of the molar mass. Oh, we actually hadn't done that one yet. Okay. So the KOH is potassium 39.10, oxygen 16.00, and hydrogen 1.01, all added together to give us the amazing 56.11. That's that ratio. Now that I've got things set up, I can just let the calculator handle the math, multiply the tops, divide by the bottoms, bam, bam, bam. Let's go to the next page for number 8 and for number 11 and number 12. So in number 11, we had 8 moles of iron acetate, and number 12 we have 1.1 moles of nitric acid. So if this is moles, I need to write my little dimensional analysis thing so that this unit is on the bottom, moles. And what am I looking for? Grams or particles? Well, according to the question, I'm looking for grams. So I need to fill this in with 1 mole and the right number of grams. Let's go back and find that value. Here it is. This is the same compound. So 232.98. 232.98 grams represent 1 mole because 232.98 is from the periodic table. Then I multiply these two values together. That's going to involve a calculator. I don't know about your brain, but my brain can't do this type of math in my head. Oh man, now I'm trying. 8 times 2 is 16, but there's extra zeros. So it'd actually be like 2 extra zeros, and then there's a 3 and a 4. That'd be 2. Oh man, why am I doing this? Alright, let me just grab my calculator. Just a second. 8 times 232.98. I was in the ballpark. I was getting pretty close. 1860. 1860 is a pretty good answer for that one. That's a lot of grams. That's a lot of mass. It's over 1 kilogram of iron acetate. But that part's not too important to us. Just getting it set up correctly, using the right dimensional analysis values. Number 12, pretty much the same thing. We have moles, so our equivalency should be written with 1 mole on the bottom, and then the mass on top. We have actually worked out HNO3 before. Let's find it. There it is. HNO3 was 63.02. So I have 63.02. It's 1/10 times 63.02. That's just 6.3. Just move the decimal, but grab a calculator if you need it. 0.1 times 63 is 6.3. This has 2 sig figs. That has 2 sig figs. And I move on to the next set of questions. Express the following in moles. Oh man, look at all this nice typed comments I have over here. Let's read these comments. How do I know what to put on the bottom in my dimensional analysis work? Very common question. I can hear at least 2 or 3 of you thinking it right now, even though I'm in the past and you're in the future. Well, I guess technically you're in the present, but I'm talking to you from the past. Anyway, how do I know what to put on the bottom in my dimensional analysis work? Let the units guide you. I have said it again and again and again. If you take the units and write them down, the units and write them down, the units and write them down, they force the next step. This one is grams. Whoa, that was weird. This one is atoms, so the bottom has to be atoms. This one is grams. The bottom has to be grams. This one is grams. The bottom has to be grams. So if you let the units guide you, it's a lot easier to set up. You only have two ratios you can put in there in this nice box down here. There was a nice rectangle before somebody drew on it. And the two ratios are 1 mole is equal to the molar mass on the periodic table, and 1 mole is equal to 6.02 times 10 to the 23rd pieces of whatever the heck it is. In number 14, since we're dealing with atoms, we're going to pick this thing. Atoms are a piece of matter, and so I used Avogadro's number on the bottom, 6.02 times 10 to the 23rd, and that's equal to 1 mole, which is why 1 mole is on the tippy top. Then I let the calculator handle the heavy math. Parentheses, 1.5 times 10 to the minus 10 to the 26th, close parentheses, times 1 divided by parentheses, 6.02 times 10 to the 23rd. Calculator does math. Answer pops out. Atoms divided by atoms cancel each other out, so we just have moles left, which is why the unit mole is left over in the answer. Number 16, we have grams. So if it's grams, then we need to use the molar mass. Alright, grams are equal to the molar mass. Where did I get that molar mass from other than the periodic table? Let's see, SCCl3. Nope, we hadn't done that one in the beginning. Since I haven't done that one in the beginning, I would have to work it out. I'd have to look up scandium, 3 chlorines, add them together, and get myself a molar mass on that one. I'm betting the molar mass is 151.31 because I typed it up. Then I divide the given mass, 302.27, by the 151, and I get the moles. I'm actually going to do question 17 on the next page, so I will skip that for right now. And number 18, the only piece that's missing here is that molar mass, which we would just need to fill in. I don't have that one either. That's annoying. Let's go to 17 though. 8.8 grams of potassium carbonate. So 8.8 grams of potassium carbonate. Yep. Potassium carbonate is K2CO3. So I've written my given. I'm trying to convert it to moles, so this should say 1 mole. And the bottom should be what unit? Some people immediately think the unit. Other people pause. Doesn't matter who you are. If the given unit is grams, then the next dimensional analysis has to have grams on the bottom. So, and then we just need to fill in a number there. Anytime we have 1 mole in grams, the number for grams comes from the periodic table. So we got to grab the pieces from the periodic table. Here's the mass of potassium on the periodic table, but you know what? I'm going to multiply that one by 2 because there's 2 potassiums. And then here's the mass of carbon on the periodic table. Now carbon has a mass of 12.01. There's only 1 carbon, so I don't need to multiply that by anymore. And then of course oxygen. Everyone knows oxygen is 16.00. Multiply that together, and I will be able to find the mass of a mole. According to my space age technology calculator, it is 138.21 for the molar mass. So all I've done right now is I've set up the problem. Now it's time to actually solve the problem. 8 grams is a whole lot less than 138.21. So it's way less than 1 mole. So I do 8.8 times 1 divided by 138.21, and my space age calculator from the future does 0.063671224 this has 2 sig figs, so I'm only going to write the first 2 sig figs. It says 0.0636, but when I round a 6 up, when I round that 6 up, it's going to be a 4 here. So there we go, 0.064 moles. Awesome. That was the answer to number 17. Carefully writing the given down, then putting the dimensional analysis together, realizing that grams come from the periodic table to represent 1 mole, then calculating the math. Whew. 19 through 23, very similar process. We are trying to find the pieces. It's going to be a whole lot of Avogadro's number in this one. And number 19, we have grams. In order to get to the number of pieces, I have to change these grams into moles, and then I have to change moles into particles. Number 20, I have 0.3 moles, and since I have moles, I can go right to Avogadro's number. 21, I have 0.257 grams of cesium chloride, so I've got to get a molar mass. I think that molar mass was worked out on the very first page. There it is. Yep. I worked that molar mass out in the first calculation. No need to do it again. I just flipped back a couple pages and found it. Wrote it down in there. My best handwriting right here. It's my best handwriting right there. And then I have the ratio to cancel the grams out to convert it to moles, and then the moles to particles. Number 22, there were 2 moles of gallium sulfate, so I could just use Avogadro's number to convert it over. And then 23, same deal as number 21, I had to change the mass to moles before I could do the conversion. Whew, finally time to do something different. If we're doing a percentage, percentages are all the same. It's always the piece you care about divided by the total, and then you multiply it by 100 to figure out your percentage. And number 24, the piece we care about is nitrogen. I would like to point out there are 2 nitrogens, because that 2 distributes. So there's 2 nitrogens divided by the total. I then go to the periodic table and I grab the values. These are the values from the periodic table. 2 nitrogens, and the total is on the bottom. The total comes out to 331 on the bottom. So when you do this divided by the total and you multiply it by 100, you get 8.46% nitrogen. In 25, you're doing the same thing but carbon. So the top is 2 carbons, and the bottom is the whole thing, the NH4C2H3O2. It's all of that stuff. The entire compound is on the bottom. And then, of course, because it's a percentage, you multiply those 2 values by 100, and you get 31% carbon. I'm going to come back to 26 and 27 in a minute. There was one other topic that we discussed in the notes and on one of the worksheets. It somehow doesn't really make its way onto this review sheet. So let's talk about the difference between molecular formulas and empirical formulas. Molecular formulas and empirical formulas are similarly related. They have ratios, but those ratios might be reducible. So here is a really common compound that you have in your life, C8H18. Both of those numbers are divisible by 2. If you divide them both by 2, you'd have C4H9. And so this is a molecule. An empirical formula is just a reduced ratio. I don't know if you can hear the background sound effects, the jingle jingle and waggle waggle. That is my dog. She is having a good time scratching. Yep. So molecules are the actual ratio of atoms, and empirical formula is a reduced ratio. So this is octane, found in gasoline, and gasoline is made up of a whole bunch of C8H18s, or octanes, And then if you reduce the ratio, you've got something that is not really a formula. You can't do this Lewis dot structure. You can't go carbon to carbon to carbon to carbon. There's not enough hydrogens there to make it work, because that thing doesn't really exist. And so empirical molecular formulas are a ratio that might not really even happen. The molecular is the actual formula present. I'm going back to 26. We talked about this as being a bonus question this year because the schedule's been kind of messed up. But here we have the mass of mercury and the mass of oxygen. First step is to change those masses into moles. So I'm using the periodic table to convert them into moles. Now they are in moles. The second step is divide by the smaller value, or smol. If you took out these two moles, this is definitely smaller. 28 is less than 56. So we divided them both by 0.028, and we got two whole numbers. If you have whole numbers, you're done, because the last step is usually get to whole. 27 is the same idea. We have a mass, we're dividing it by the molar mass to get moles. A mass, dividing it by the molar mass to get moles. This one is smaller. Divide them both by the smaller to get to the number of moles. Okay, I hope you've practiced. I hope you're ready. I'm getting excited. You're going to need a periodic table and a calculator to do this stuff. You're also going to need a lot of practice behind you. Have a good time, good luck, and may all of your rounding be perfect.